be talking about conservative versus non-conservative forces.
Conservative versus liberal.
Oh.
Your forces would be more conservative.
Depends on what each one means, bro. Is conservative like they hold back?
No. Conservative is in science the same thing as it is like conservation of energy, conservation
So it doesn't like use all of its force?
No, not that kind of conservation. Like it can't be created or destroyed.
Oh.
Okay, so a conservative force is a force whose work so remember the relationship between work and force. Is a force whose work on an object is independent of the path of the object. So I'm going to let you write that down and then I'll explain that in English.
Okay.
So the greatest example of a conservative force is one where the object begins and ends at the same place. And so in that case, what can you say about your displacement?
It's zero.
Right. So the perfect example of a non-conservative force in action is the roller coaster.
Oh, okay.
And so you have to get on at a fixed point and off at the fixed point.
Yeah.
And the work that is being done on the object doesn't matter if you are on, like, have you guys been to Great America?
Yep.
Do you like riding on roller coasters?
I'm not a big roller coaster.
Okay, so Carter, for you, you'll be able to understand this. The forces that are acting on the object, like so you, when you're riding on Raging Bull, are the same as if you were on a different roller coaster. I don't know if I think they got rid of it. They used to have a roller coaster that was called Iron Wolf, where you were standing, like you had like this little, I know, it was like a little bicycle seat that you like put like.
Oh, that's like Green Lantern now.
Is it? Oh, yeah,
That
but
was terrible.
like, doesn't that the one where you like tilt forward? Oh no, that's a Superman.
Superman's one's that we're.
Yep, where you're
But,
like laying on your
I
front.
feel like I would already.
I was just last time I went, I was too small for a lot of them, but I still went on all ones I could.
My mom barfed on Raging Bull the last time my folks went to Great
I
America.
did go.
That's like what I'm
wait,
scared
Rainbow Bull's
of,
the super tall one. Right?
Yep,
Yeah,
yep.
Raging Bull.
Yeah.
I feel like you throw up and then I like fall.
I was about-
And then she was in the bathroom cleaning herself up, and some young girls came in the bathroom and were like, "Did you see that old lady barf all over the rock?"
She's like, oh.
Oh, that's me. Okay, so some other examples. Gravitational force or gravity is conservative because it doesn't matter. I mean, gravity affects you everywhere. It doesn't matter where you are on Earth. You're gonna always be your butt in the seat.
Yep.
Let's see. The elastic, can't spell, spring force. We'll get to that in a few units. But that makes sense because, like, so on like a keyboard, for example, all of the keys have little springs underneath them, and when you press it down, then it pops back up. And it makes sense to us that elastic spring force is conservative because the spring has to return to its original.
Like a rubber band.
Yep.
Okay.
The electric force is also a conservative force. And we don't really spend any time talking about electricity in AP Physics 1.
Springtrap?
What?
Oh, you guys don't know.
No.
You guys not watched the Five Nights at Freddy's movie?
No.
I just know Josh.
I know, Nina. I know you. Of course you know Josh and I, because all you care about is men who look good. Especially, oh my god. She posted a thing in her story about the quarterback. from,
Yep,
the
Sam
game.
Hartman. He's so hot. It's crazy.
I-
It's crazy. Even straight men know that. Like, it's just, you just need to have
like Lindsay's
eyes.
dad.
No, he does
In his-
not.
When he's in his Jesus face.
All right, let me see this man's here.
The man's is hot. It's crazy.
Okay, so here are all your examples of non-conservative force. The tension force, friction, air resistance, the normal force,
Okay, let me show you this man.
and then propulsion.
So what's the definition?
Exhibit A.
This is the definition.
Exhibit A.
All right.
Who's
Exhibit B. Exhibit C.
Okay, the mullet though, not so much. Yes, I like the fresh cut. I like go back one.
This one?
Yeah, that's much better than man.
No.
man with a-
Oh, he's so hot.
Man with a mullet is an automatic thumbs
That's
down.
not really a
You
mullet.
cannot be attractive if you have a
I
mullet.
don't call it a mullet though. I call it
It's like a,
oh, there's some with a mullet.
Yeah.
But
It's
there's
a-
some with when he
yeah.
has the full,
Yeah.
like the full long. That's not really a mullet because it's like all the way around.
right, but then when this is when
And
it's
when he cuts the sides,
business in the front,
when he cuts the sides and yeah, there it is. mullet.
it's
I don't
it's
care.
not
He's
good.
hot
There,
every
see,
single
that's
way.
not a mullet.
This one.
That one's not a mullet.
It's all right. He's all right.
No, he's so hot.
7.5.
No, no.
Okay, let's put a picture up so that Lindsay, when she views this.
You gotta scroll through them.
Okay, so Lindsay, you have to decide.
Gave Elvis a 7.5.
And you can scroll the other way.
Oh,
Yep.
I like this one is much better than
That
the
one's so
free flowing
hot.
mane. Yeah,
That's
see,
the
a
one-
mullet man, no, thumbs down.
That was hot.
This one's looking nice. But I mean, any man that's dressed up like that,
And that's it.
and that's it. Okay, so Lindsay,
Oh.
you can decide. Thumbs up, thumbs
He's
down.
Nina,
so
Nina,
hot.
What's your rating?
I feel like if I lived in that age, I feel like I would definitely think I was hot.
Yeah, what's your rating of Lincoln?
Now?
That picture.
All right, let me
This
see.
picture?
So when you
Let me see Elvis.
I don't know.
I mean,
Give him like a
He's not bad looking. He looks a little effeminate.
Well, he did. I think.
I mean, I'm not gonna lie,
He wears
but
makeup, yeah.
yeah,
Some-
the
I
eyeliner
like
is
a lot
just
of-
a little bit much for me.
Yeah, and your rating.
Yeah, I said 8.
Oh, 8? Damn, that's high.
It's like 7 or 8, you know, it's okay.
What about 1977 Elvis?
Okay, that's not good.
Okay, don't blame me.
let me see old
he's on,
Elvis.
He's on drugs and almost dead.
He was going.
Yeah, yeah.
Chunky Elvis. What about this Elvis? 70s Elvis.
I feel like the first one was. Okay.
Well, yeah, because by this point he was like 30.
That was his peak.
Okay, so when you have a non-conservative force,
Oh man.
you can state that these properties are true. Okay, so this is not that bad. It's not really as bad as it seems.
Kinetic energy.
So really what you have here is delta KE plus delta PE. So what you're saying then is that the work done is equal to both the change in kinetic energy and the change in potential energy.
Yep.
So you have to take all of that into account when you have a non-conservative force. This is the same thing, like what you're really saying here is what we know of from chemistry as some substances' internal energy.
Okay.
It's the sum of the kinetic and potential energies. And so you can think about that as something that you already know. Okay, so if this is true, we can also say that. So I'm just going to take this formula that from above here, and I am going to reorganize it a little bit. I just have to think about how I actually want to do that though. how do I want to do this to make this? Okay. So what I'm going to do is,
What is that for?
it's this song that's playing on the Christmas channel. It's really annoying.
Yeah, what is it?
It's somebody's interpretation of some terrible music. Okay, so what we're going to say though, the work that is done by the non-conservative forces, if this is equal to 0, we have 0 joules there. What I can do is rearrange my equation so that I put positive terms on one side and negative terms on the other. Okay, so what that means is on the left side of my equation, I'm going to just move my subtracted things over to the other side. So that will make them now positive. So potential energy initial and kinetic energy initial are going to be on the left. And all I did there was just do some manipulating with my algebra.
Okay, yeah, that makes sense.
And now if I use this formula and because I don't really a lot of times know what kinetic energy is or potential energy is, but I know their components, I can use what I know about those equations to create this formula for myself.
That's wild. Oh man.
This is pretty important. We're going to do a lot of work and a lot of problems using this formula because it's something that you need to be able to have a really good command of. Right now, we only know about the energy of a system that is from its motion or from its position. Later on, we will learn about energy from its rotation, and then we will learn about energy if it is a spring. So this is not all of it. There are really actually 4 components of work or of internal energy. We just only know the first 2 of them so far. So I'm pretty sure on your formula sheet, there is a formula, excuse me. Yes, in Unit 6, if you take a look at the one that I made for you, at the very bottom of Unit 6, there's this big ass formula here where it says E equals 1/2 mv squared, that's kinetic energy, plus 1/2 I omega squared, rotational energy, plus mgh, potential energy, plus 1/2 kx squared, spring energy. And this is only 1/2 of the formula. So you would have all of them final equal all of them initial. And the reason we can say that is because energy is the conserved quantity. It can be neither created nor destroyed. Therefore, whatever you had at the beginning, that has to be equal to what you have at the end, if you're taking all of the components into account. Okay, so let us do a couple of examples real quick. Let's start with number 29.
In the book?
Yep. This is on page, I think, 184.
I think so too. Let's check. Carter was right. Is that Taylor?
Is
Yeah.
what, Taylor?
No, I saw this picture of a girl singing.
That's the
Let
thing.
me see
Poor
if I can
Carter.
find it again.
That's the thing. She can't sing.
It is on 184.
I mean, her music's not terrible.
I don't think so either. I'm not the biggest fan of her,
I mean, it's not bad.
but
I'll listen
I
to
think
it. It's
But
not bad.
There's so many women with such better voices.
I think, but she just is the most brilliant marketer of
yes,
our
the
time.
marketing
That's
team
the only-
crazy.
I don't think I don't know if it's her. It's probably someone else doing it all.
That's why I'm saying the marketing team, the marketing strategy.
She is just capitalizing on all of the. It's a perfect storm for her right now, and
I don't even really think she's
The thing is, women as fans, they're so dedicated and loyal
Yeah.
to it. So if you have a big women fan base, it's just whatever you
the
do.
brand loyalty, yeah.
Whatever
And,
you
and
do
she
is
just
gonna
has
be
been able
successful.
to brand herself.
That's the truth of a successful artist. If you have teenage girls screaming for you, you're successful.
I mean, that is true. I mean, look at throughout history. I mean, we were just talking about Elvis. He couldn't have had nearly the heights of fame that he had if he wouldn't have had all them screaming girls.
Mhm.
The Beatles.
right?
Literally everyone. I
Yep.
have on the Ed Sullivan Show. What do you hear every time? Screaming girls.
Screaming
Yeah,
girls.
like young women are the most vulnerable.
Throwing their
because
panties.
They're just throwing their money away.
Yeah, their panties.
You're right.
All right, so let's do number 29.
Okay, I can't find the girl anymore.
We need it's on page
Alrighty.
184.
I know, but I can't find the girl anymore.
Okay, number 29. A 75 kilo. Oh, this was written way before. This is a copyright way before Taylor Swift. A 75 kilogram skier rides a 20 blah 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 meter long lift to the top of a mountain. The lift the angle makes. Oh, blah blah blah. I can't use words. What is the change in the skier's gravitational potential energy? Okay.
That equals 75.0 kilograms.
Okay, Carter.
I did not.
I do not have sexual relations.
No, the
That one.
JFK from Clone High. It's just he has the dumbest JFK voice. Nothing bad ever happens to the Kennedys.
Remember when we watched the JFK assassination in 8th grade?
Yeah.
And we were just subjected to that? She was just like, let me just pull it up on the screen. And we just watched
You
it.
couldn't deal with. Oh no.
We were like, oh, okay, cool.
Like I got shot 50 years ago. More than that. 57 years ago. Jeez, 70 years ago. That's crazy.
That is kind of wild.
And Miss Thomas Jessica remembers where she was.
When what?
Kind of crazy.
She remembers where she was when JFK was shot. Apparently, I will not remember JFK. Wait, that's 1963.
Yeah. Okay.
Wait,
So,
so that's literally.
well, even if, okay, so if
That's
she was,
60
if
years
she
ago.
was, well, my parents were 9.
So
My
she's-
parents, my parents are both 69.
So she's at least over 63.
Yeah.
She said she
Because
was
how
little.
could-
She said she was little, so.
Okay, so maybe like let's give her the benefit of the doubt. How little is little? 4.
I'd say at the youngest she's
So then she's got to be 65,
probably.
64, 65.
I could not imagine continuing teaching.
I hope that she stays until Matthew Unkeyzimmer graduates from college, and I would love it if he came and taught was her
Unless she took
replacement.
medicine,
I know, but
But like,
He really admires like this one professor there.
I know he does. But I think he has the ability to teach people, and a professor is not a teacher.
I don't know about that.
Mm.
Yeah. Sometimes,
No, he
sometimes
does.
he's just like, well, why do you not just know it?
No.
Yeah, but how is that different than Mrs. T?
Yeah,
True.
he'd be the perfect replacement. No, like he teaches a little bit better because like I understand some things.
I mean, he did get me through eighth grade algebra. I wouldn't have.
Pass without him.
I would pass, but like.
I think that he has the ability to actually teach.
Oh, yeah,
I think
yeah.
that he has some things to learn,
Mm-hmm.
Yeah.
obviously, but I think that he could be a good teacher.
I don't know. I don't see him as like a college professor though.
I don't.
I could eventually. Please.
I can see him as like a lifelong student, man. He's just like, you know what? Now that I got a master's degree, let's get another one.
Yeah, I could see him as a lifelong student. Yep. Okay, so here we are. We've got everything set up. Now, a lot of times when we are dealing with energy, we can cross off at least one of the terms. So if we are going down a height, what is so like really what we need to have is, because if we were to do this, we should have MGH minus MG initial. So what is our final height?
Change.
Our final height 0.
Yep. So if our final height is 0, this term disappears entirely. So now all we need to do is figure out what our initial height is. It's
I
not
thought the list was this way.
it's not 2830. Because we have to account for the fact that this angle is here. So what we really want to know is not this distance, but this distance here.
Okay.
Well, then you can just give it a walk off.
Okay, Carter.
Pythagorean theorem.
It's giving
Triangle.
triangle.
I'm gonna try to formula it and see if I get
So
it.
this is what I would do. I would say that my H is equal to my 2830 meters. And then, oh wait, no. Okay, well I know that cosine of theta is equal to, and it's not cosine.
The other
Sine.
angle is
It's sine for sure.
the other angle is 76 degrees.
Over h.
Divided by
Oh.
h. So then
you
h
just
would
switch
be
11697.
divided by the sine of theta.
Yeah. Okay. That's manageable.
Yeah, this isn't bad at all. I think that the hardest thing in these problems is going to be to read the problem and
understand
figure
what's
out the physics of it, because the math really isn't bad at all.
Because I thought the 2,830 was the h.
Yeah, but we have to account for the fact that there's that angle there, so you're actually
I didn't
traveling
read
a
it right,
farther
and I thought it
distance.
was like the lift they were writing it
Yeah.
this way, but they're going vertically up. Sir. You okay there? No. Okay.
When I was younger, so much younger than today.
What happened to the Christmas
I
music?
needed
Well, I turned it down because it was so bangy.
Oh, okay.
Wait,
So
why do you have 2830 up there divided by sine theta?
Because I know that sine is equal to opposite
Switching them.
over hypotenuse, and I'm solving for the hypotenuse.
But you can divide the whole thing by it? I thought you
Yeah.
could divide 2830 by it.
Well, it doesn't matter because multiplication is cumulative.
Well, I guess. It
He
just
guesses.
it works better on my brain.
You don't have to do it my way.
My way or the highway.
No, I'm not like that.
Okay.
That's what it's to.
That is. I remember
Yeah.
when Agata would be yelled at for like doing math the other way.
I don't feel like that is helpful because I am not the same as all of your college professors, and I can't be them. In all of my chemistry classes, somebody did it differently, and obviously took a lot of chemistry. They did it differently, and everybody had their own style of doing it, and so you adapt it to that person's style. And I think that that's much more successful because then you are able to recognize this fits my pattern, but just in a different way,
Yeah.
as opposed to, oh, it looks like something I've never seen before. I don't know what to do.
Yeah. Agata should have been in AP Calc. Like I don't know what she was doing in our class.
Only she wanted to do it.
Maybe.
Well,
that would have
maybe
been a nightmare.
maybe with the language and everything.
That really would have been a nightmare if she ended up doing
Negative
AP Calc and having to do it. Like learn a new thing and do it
859.
her way too. Oh.
Negative 8 million?
What?
We'll use scientific notation.
Negative 8.5. Negative 8.6.
Times 10 to the
Times 10 to the
6.
Wait, why are we dividing by?
Wait.
What happened to 2?
6, yes.
It's here.
Okay, wait. If we're finding,
Ooh.
why are we dividing by sine?
I'm looking for the hypotenuse.
I thought the hypotenuse would be just 2830 over sine.
Yes, but that's what we did.
Yeah, and I got
Yeah.
11,000.
We can multiply them by 9.
Oh, well then you have to put it back into this formula.
See what she has up on the board, Nina. Maybe if you look at the board.
I'm looking at the board right now, Carter, bro. What are you talking about?
Sorry, Nina.
So wait, this is. I understand like we have to plug in all that stuff to find like theta of potential energy, but I don't understand why we're putting it over. Like why we're dividing it by sine.
Oh, so in my formula here, I've got mass,
Uh-huh.
gravity,
And then the height. Yeah.
and then the height, but I said that height was equal to 2830 divided by sine of theta. So I can write it like this, or
Or I could just multiply mg by the 11. Okay, got it.
yes, but if you calculated your 11 whatever,
Yeah. Okay, that makes a lot more sense.
or what Carter didn't like about the way I done this is that he wanted to put
Well, I said it.
sine of theta. It was confusing to you.
Yeah, I got
It
it.
does make a little bit. more
It-
sense.
It doesn't matter how you do it. Multiplication is cumulative, so it doesn't
Yeah.
matter the order. once you followed order of operations.
Okay, yeah,
It's
okay.
fun. It's so
Then we
fun.
all got a
What's
big
yours?
number.
Alrighty, so then let's see what other ones that I want to do.
5, 6.
Let's look at number 37.
Let us. Wait, what would be the? Is it just meters then?
It would be
No.
joules.
Joules. Yeah.
And that's why you got such a big number there, Carter, because it's not in kilojoules.
No, 2 joules anymore.
Joules is a pretty small number. Like it's a small measurement.
I'm pretty sure Jules got Jules shut down now because of all
The lawsuits or
Yeah,
whatever.
and all the lawsuits.
All right, let's look at number 37. A gymnast is swinging on a high bar. The distance between his waist and the bar is 1.1 meters, as the drawing shows. At the top of the swing, his speed is momentarily 0. Ignoring friction and treating the gymnast as if all his mass is located at his waist, find his speed at the bottom of the swing.
I don't like that.
All right, so
I like how
all
we're
we
doing
get
one number roll.
is
The
distance
radius.
is 1.1.
Okay.
All right, so I know that this is a conservation of energy problem because I've got something that is in motion, but then is also stopped at some points. So if here is the bar that he's swinging around, here is his waist.
Yep.
At the top, velocity equals 0. What does it equal at the bottom?
Whatever it's supposed to.
That's what we're trying to figure out.
Yeah.
Okay, so a couple of other things that you know. So we can call this velocity initial. We don't know his mass, but I am looking at my conservation of energy formula and I see that mass is a term, is part of every single term of that. So that makes me think I probably don't need it, or I can make my algebra work without it. The other thing that I do know is that I've got, like, I can figure out what the height is. So what is the height here?
0.
And then what is the height at the top?
1.1?
No.
No.
Because it's only one at.
Wait, I'm confused. Why wouldn't it? Because it's the radius.
Because that's the radius, but the distance from height 0.
Oh,
Just
2.2?
2.2.
Yeah.
Oh, okay. I see. That's okay.
Okay. So let's take a look at this. Okay, I solved mine a little bit differently, but that's okay. It'll work out. So I'm going to write my formula for conservation of energy on the board.
Let's see it.
And now I'm going to hope that I can cancel stuff out.
What happened?
So what do you think can get canceled?
Well, let me write this all out.
The
Okay.
one with the velocity.
Okay, yep, so velocity initial
Yep.
is a 0.
Why is there
And then there's height is 0 at some point. So
why is there
the
2 in the data?
MG
What's that true?
It's not there.
Oh, this is 0. I'm just saying that this whole term here is canceled because it's
Yeah.
0.
It's MV initial squared.
Mm-hmm.
Yeah.
Yep, 1/2 mv squared is your kinetic energy formula.
MGH initial. The MGH initial 2 can be crossed out. Wait.
What?
Yeah, because
Mm,
yeah,
final.
final.
That's last second.
Okay, so now I've got a much more workable situation here.
Okay.
And I am going to go back to my drawing and think to myself, what am I looking for? V final. So let's just solve this thing for V final.
So 2 V final equals square root of GH initial over, out of 2GH initial over 2GH initial.
Yeah, I did the same thing. Yes, sir.
Look at that. Don't have to divide by anything, you know?
And so you can see that if you are going to do your algebra before you put numbers in, this actually becomes pretty manageable.
Yeah.
And it's even something that if you had to do without a calculator, you could get an approximate value.
6 point.
You can say that 10, you can like just round these numbers a little bit. So 2 times 10 is 20, times 2 is 40, square root of 40. You could even think of a number that's close to that if you had to without a calculator. What did you get for an actual answer though?
6.57.
And what's your unit here?
Meters per second.
Correct.
Also joules just because.
So the physics of the problem, this would be physics,
That's the hardest part.
this would be physics, the rest of it is math.
See, math is not the problem.
The math is not the problem. The math will never be the problem. It's trying to turn the stuff that they say there into a picture that makes sense to you, and then wrapping your mind around the fact that you're given literally one piece of data that you didn't even use anywhere in your math.
True. Except to find the distance.
Alrighty, so the homeworks. This is homework number 18, I think, but it also might be 19. I'm pretty sure. 30, 34, 38, 44, and 45, and then 46 is an extra credit friend.
Is she really a friend?
She's a bitch.
She's a backside bitch.
Let's see. What number did I say was that? 46. Oh,
She's a bitch.
she's a real bitch.
She's a bitch. I'm not doing her.
I don't do bitches.
Okay, Carter.
well played, Carter. Well played.
All right, can we grind this out?
Yes, you probably can. The first
Juggles
couple,
and Bengals are clowns.
the first 3 I would say are pretty simple.
Did you say juggles and
It's
Bengals?
literally
Yeah,
the
juggles and
names.
bangles.
Read it.
The Bengals are clowns this year.
Yes, they are.